Hi everyone, today we're covering Newton's method, which is really useful. And we use it for, it's basically an extension of our tangent line approximations that we did yesterday. And it helps us to find the solutions of a graph. And it can help us, especially if it's kind of a complicated graph and we're not sure how to do it, it can help us out with that. So first, we're going to derive the formula for Newton's method. And in order to really understand what's happening, let's take a look at it graphically. So say I have some curve, okay, nice curve. Okay, what I'm going to do is I'm initially going to pick just a random kind of guess point, right? So I'm going to pick a point, and we're going to call that x sub 0. Okay, what I'm going to do is draw a tangent line at that point. Okay, so essentially the goal here is to try to figure out where this curve crosses the x-axis. I'm trying to find the solution for this curve, and I'm going to approximate it by using Newton's method. So first we just start with a guess. We take the tangent line and I see where the tangent line crosses the x-axis. Okay, now I'm going to keep going. So now I'm going to take wherever my tangent line crosses the x-axis, and that's kind of like my new guess. So this is my new point. I'm going to call it x sub 1. And I'm going to draw another tangent line at x sub 1. So I get another tangent line, goes that way, goes over here. And if my pen wasn't so thick, it wouldn't look the exact same. It looks pretty similar, but I'm not quite there yet. And then wherever my x1 tangent line crosses the x-axis, I'd pick that to be my x2. And then I would keep going, and I would keep going, and I would keep going. And kind of the question is, when do you stop? And generally, you'll be given like a maximum error. And so when you fall within that boundary, then you would stop. But essentially, you can keep going and keep going until you get pretty much the exact answer, but not quite. Okay, so how can we put this in equation form? Because it's all nice that we have this graph, but if we can't do it algebraically, then it doesn't help us that much. So here's what I know. Okay, so I'm going to think about this in terms of x1 and x0, x sub 1 and x sub 0. So I know that x sub 1 corresponds with a y value of 0. Okay, so I'm going to assume that the tangent line for x sub 1 was pretty close. So what I'm going to do is write my tangent line. Okay, so what I can do is, so say I have a y value of 0 minus f of x sub 0. Okay, so this is, I'm kind of like writing my tangent line using x sub 0 as my point. Okay, so here's my y value minus my second y value, so y2 minus y1 equals, and then my slope is at x sub 0, that was my initial guess, times, I'll say x1 minus x sub 0. So this is essentially just my point slope form. Here's y2 minus y1 equals m times x2 minus x1, but we're using x sub 1 and x sub 0 instead. Okay, so what I can do is, this is just 0. I'm going to divide both sides by f prime. So I get x sub 1 equals x sub 0, x sub 1 minus x sub 0 equals negative f of x sub 0 divided by f prime of x sub 0. Okay, and I want x sub 1 by itself. So I can add x sub 0 over. And what we have here is exactly what I did here graphically, but in algebraic form. Okay, so my new x1 is going to be my old x value minus the y over my slope. Okay, and that will keep moving me down and down. So this is my overall equation for Newton's method. Now, this is pretty specific because it's using 1 and 0, so we're going to rewrite it in more general form. All right, so what I can say is x sub n plus 1 is equal to x sub n, which is 1 less, minus f of x sub n over x prime of x sub n. Okay, and what we have here is called a recursive equation, okay, as opposed to an iterative equation. And a recursive equation just means that you need to know what x sub n is so you can find x sub n plus 1. So you need to know an old term so that you can find the new term. Okay, so we need to start with a guess so that we can get a better guess, and then a better guess, and so on. And then again, it kind of like, when do you stop guessing? When do you stop? Okay, so let's move on to an actual example, and I think it'll kind of help you out. Okay, so this says TI-89, but this works just fine for TI-84s, and I'll show you. But this kind of gives you just a rundown of what we can do to help us, let our calculators help us. So first, we're going to use Newton's method to approximate the zero of my trinomial here. Or it's not a trinomial, but my cubic function. Okay, and I'm going to continue doing iterations until two approximations differ by less than 1/1000th. Okay, so this is typically something that you'll see. You'll have some kind of like maximum error or whatever. Okay, so this is my starting point. This is my guess. So my function is here. I need to know the derivative. So we get 6x squared plus 2x minus 1. Okay, so what I'm going to do is take my calculator and type these in. So my y1 is going to be my original function. My y2 is going to be my derivative. And in my calculator, I went ahead and already did that. That's not my calculator. Here's my calculator. So if I went to y1, and this is from the next example, but in my y1 and my y2, I have my two functions. So what I'm going to do is type in negative 1.2. Okay, so I'm kind of storing that in my calculator. Okay, next what I'm going to do is do second negative to get answer there, minus, I'm going to make a fraction, and then recall my y variables, so y at my answer over y2 evaluated at my answer. And the reason why we have to use this answer instead of just saying letting this equal x or something like that is because this will keep changing because it's a recursive formula. So when I hit enter, I get negative 1.235. So that's my x2. Okay, so what we just did was we started at negative 1.2. Okay, so that was my initial guess. And somewhere near negative 1.2, there exists a 0, so where this function equals 0. And the more times I do Newton's method, the closer I'm going to get to the actual value of that 0. So I got a little closer. Okay, now if we do it again, I'm going to get a little closer even. So let's write down what we got. We got negative 1.233754. I'm going to go out a couple more decimals because we won't see the difference unless we do. Let's do it one more time. I don't know why alpha is selected. One more time. And we get negative 1.233751, we'll say. So now the difference between x3 and x sub 4 is less than 0.001. So I can stop at this point. So what we found was by Newton's method, the 0 is approximately negative 1.233751. Okay, now it's not exact, but it's pretty close. It's good enough, we decided. We decided that if my approximation started to get, less than 1/1000th of a difference each time I did an iteration, then I decided that that was pretty good. So this is my approximation of the 0. And I did that without knowing what the graph was and without having to do a whole bunch of extra stuff. Now in this particular function, it's pretty easy to find the 0. We could do that. But imagine if we have a way more complicated function where it's not quite so easy to find the 0 without using some kind of big machine or something like that. That's where this method would typically be used. And you can see that a little more in our next example where we have a trig function. Okay, so this time I'm trying to figure out where these two functions intersect. Okay, so very similar, except I'm just trying to figure out where they intersect, and my starting guess is 1.25. So what I'm going to do is set these equal to each other, because that's the intersection. And so my function is tangent of x minus 2x. That's my function. Okay, I'm trying to figure out where these intersect. So if this equals 0, that means that they intersected. So this is my function. And I'm going to plug this into my y1, just like I did before. Okay, my y2 is going to be the derivative. So if I take the derivative, I get secant squared minus 2. And so again, I'm going to take the same thing that I just did. So we'll go back to our calculator. And again, I had already plugged these in. So if I go to my y equals screen, I plug these into y3 and y4. You can do whatever, but here's how they look in my calculator. And I'm going to set up the same thing that I just did. So first, I'm going to input 1.25 as my initial guess. Okay, and then I want to do basically the same thing, except, okay, not sure what happened. Okay, except I'm going to recall y4 and y3. Okay, so I did one iteration, and so my x1 was 1.25, my x2 is 1.18675. We'll go a little further. All right, so let's do it again. I got 1.16702. Let's keep going. Okay, I got 1.165568. Okay, still not enough of a difference, so let's do it again. All right, and this time I got something really close. So 5561. All right, so now these two last iterations were definitely within 1/1000th of each other, so I'm going to stop right here. So I'm going to say x5 is my is enough iterations for me to do Newton's method. Okay, so this is my guess as to where they intersect. Now it asked me to find the y value, so all I can do is if I plug in my x5 into tangent, I should get 2.331, and it should be the same as if I plug it into 2x. So if I plug x sub 5 into 2x, I would get the exact same thing because that's where they intersect. And so my final coordinate is 1.165 and then 2.331. And if you check this in your calculator and you found the intersection on your graph, you would find that we got the same thing. Okay, so that's it for these notes. I'll see you all later.